In this video, we're going to talk about the strength of acids and bases. So to begin with acids, we can start first by considering a generic acid molecule. We're going to call this molecule HA, which essentially just means that somewhere on this HA molecule, there is a hydrogen atom, and this molecule is capable of donating the hydrogen as a hydrogen ion. So if you add this to water, the HA is able to dissociate, donating a proton to form a hydronium ion and A-. Now, as we discussed before, when you have an acid donate its proton, what's left over, the A- is what we call the conjugate base. So again, the conjugate base is what's left over after your acid has donated a proton. Now here, the conjugate base is actually really important in determining the strength of an acid because acid strength is directly proportional to the stability of the conjugate base. So we say here acid strength is proportional to the stability of the conjugate base. And the reason why is because if your conjugate base is very stable, it's just going to sit in solution and do nothing. However, if your conjugate base isn't very stable, it's going to want to pick the proton back up to reform the acid molecule. And in that case, you're not forming as many hydrogen or hydronium ions as before, so that's not as acidic of a solution. Okay. Now the next thing we can talk about is the strength of an acid can be quantified. And the way you quantify the strength of an acid is by looking at the equilibrium constant for this dissociation. And here, since we're looking at specifically the dissociation of an acid, we call this the acid dissociation constant Ka. But just as before, this is simply just the equilibrium constant expression for this reaction. So we've got products over reactants. And again, we're leaving out water because our equilibrium constant expression excludes solids and liquids. So this is our expression for Ka. And as I said, Ka is a measure of acid strength. And specifically, we can say that Ka is directly proportional to acid strength. Now, this should make sense because if you want a strong acid, you want to form a lot of hydronium ions in solution. So if you have a large Ka, that means you have a lot of hydronium ion in solution. Compared with the opposite, if you have a small Ka, that's a weak acid because then you don't have very much hydronium ions in solution. All right, so this is one measure of acid strength that you're going to want to know for an MCAT. There is another measure of acid strength, and that is very similar to Ka, but what is called the pKa. So pKa is equal to negative log of Ka. So at this point, you might recognize from saying pH and pOH and now pKa that the lowercase p simply means negative log. So pKa is simply the negative log of Ka, and what you need to know for an MCAT is that pKa and Ka are inversely related to each other. So that would mean that acid strength is inversely related to the pKa value. So overall, we can say if you want to look at the strength of an acid, you're looking for the Ka and the pKa values. And specifically, a higher Ka and a lower pKa value indicates a stronger acid. Okay, so that's acids. Let's take a look at bases. Again, for bases, we can consider a generic base, which is just some molecule in solution that when added to water can accept a proton. So when it accepts a proton, we are left with BH+, and a hydroxide ion. Now here, BH plus is what we call the conjugate acid. Remember, the conjugate acid is simply the base after it has accepted a proton. So this is the conjugate acid. And very similarly to acids, the conjugate acid is very important for determining the strength of the base. Specifically, we say that base strength is proportional to the stability of the conjugate acid. Proportional to the stability of the conjugate acid. All right, so the more stable the conjugate acid, the more this reaction can proceed, which means more protons are accepted, stronger base. And similarly with an acid, we can quantify the strength of a base looking at Kb, the base dissociation constant, which is simply the equilibrium constant expression for this equation up here. So again, we've got products over reactants, excluding the liquid, and this Kb value is important because it is a measure of base strength. So we can say here that Kb is directly proportional to the strength of a base. The larger the value of Kb, the more protons that have been accepted in solution. Similarly, we also have pKb, which is simply the negative log of Kb. pKb, again, is inversely related to Kb. So if we're looking for a stronger base, we're looking for a smaller pKb value. So pKb is inversely related to base strength. All right. Now, one last relationship that's important is when an acid donates a proton, its conjugate base can have basic properties. Similarly, when a base accepts a proton, its conjugate acid can have acidic properties. There's a way that you can relate the strength of an acid to the strength of its conjugate base, and similarly relate the strength of a base with the strength of its conjugate acid. And that's what this equation right here, which is pKa plus pKb is equal to 14. And you can also use this other equation, Ka times Kb is equal to 10 to the negative 14. So a couple additional relationships that you want to keep in mind when you're looking at the strengths of acids and bases.